Yeah. Then next, I'll proceed to integrate the structure necessary using this Device Studio platform more practically. The first is the residual A of electrode-electrode type aluminum-aluminum. What's the matter? It's done. This is what we just introduced. It looks like this. It is in the structure of aluminum shoes, and then we have to slice it. Then let's take everyone first to create it together. First, we cut him one by one, and then now this place is a face-to-face operation for him, and then we have to ensure that he has that periodicity during face-to-face. That is, he has a minimum period. Then first, stole it. After the demon face, she was in such a state now. Indeed, not pure package structural design components, they're central amid transformative functioning. We already defined classroom. And in this place, we can treat him broadly, and then we can turn it into a twin structure from this place. We can preview it as it has entered this package-proof state due to our operation, and subsequently construct it. We got this material, which is now in the state of a square package, and then when we finally want to use it, we have to carry out an expansion operation on it. Expansion can occur along the x-axis and actually in all XYZ directions. Elections in this spot are viable. Regarding the specific process, feel free to explore this. Further details are also found in the Device Studio instruction manual. Here, we provide a straightforward demonstration for you. We can expand the bag on both sides in this X direction, huh? Consequently, the result obtained also implies feasibility on our end. For now, let's preview it in advance. Then build. This looks like this now. Because we have to consider an adaptation rate when setting up the device room, so we also have to operate one for it. That what? We delete the atom this time, but when we delete it, it also ensures a periodic structure. We can take a look at it later. If we delete this layer of atoms, then the principal on its boundary is in this position. We can see the position of its principal here. That is after we delete, because if it is expanded now, it won't have that strict periodicity, and then we have to copy this value first. After completing the replication here, particularly in this region, specifically in the X direction, we notice discrepancies in copying. Just click on this coordinate. Then we will change the direction of X in this place. After the change, he is in this state now, and he is still a strict weakly structure. Then the atoms on its boundaries are equivalent. That is, you can create them yourself later, or follow my operation to walk through the process. So we get this comparison material that we are going to use at last. Well, let's talk about it first and put it here. Given the strictly periodic nature of its structure, we will now introduce the primary cell of alumina in detail. 10,000 miles are in this. After we import it, we can see that it is not a cap placing structure, and then we also have to cut and wrap it, just like the operation of the brigade just now. Then we will also demonstrate it to you here. First of all, it is to put a 001 cut slice into it, which was just introduced in that pat, and it is also introduced that everyone can. It's okay to go back and have a look later. It's also necessary to ensure that it has an acute structure in this place, so you can think about it in this place. Now we get this, which is pasted, and then it is the waste surface of the aluminum finish, and then it looks like this after cutting it. If he goes to match it with the donkey, he has to turn it into a cat sealing structure with this re-deep crystal. We can think of this parameter. Preview shows him as a helper, utilized in construction for enhanced efficiency. It can be seen that its current coordinates are still much different from that of the woman, so we have to make a test on it. Well, you can just look at the comparison. This is aluminum oxide, and then this is aluminum. Now, its amount will be relatively different, so we perform a conversion operation on it in this place, which is to make an exchange of its X and Y amounts, and then we don't know the value here.
Adaptation 7.
Well, the main reason to continue in this place is to match its golden pavilion with lewd as much as possible. And then now after the exchange, it becomes like this, or this must be that if you build a model, it may not work. So you have to use this rotating button in this.
Then you can select all atoms first. Post-atom discussion, employ rotation tools effectively for alignment accuracy.
Then it can be changed in this place, which direction it is along or along that axis. And then this place can set it at will to turn to the degree. And then here we are.
Well, adjust it to 90 degrees precisely. It is meant for him to integrate this atom into his scriptures effectively.
We grow around the time together, and now it becomes like this. After we get such a structure, we concentrate this atom, and now it is completed. That is, we have obtained a comparison to if the materials are matched, it will be a more regular structure. Then here we use the redefine cholesterol button to perform an expansion operation on it. Well, because we can expand the package, and this can reverse the book transportation competition. That is, the J direction is a smooth direction during our period. In the J direction, you can choose at will, that is. You can preview it, and then if you want to be long, it will be on the right.
That is, it is also periodic, this extension to replicate. Well, in fact, if you choose 4 here, please have a look. He extends towards the right until the end, and we can select 2 options initially.
This is mainly when we create the model with different thicknesses later. When we will create different thicknesses, because we have to intercept from this material, we have to be in this place, include some, and then ensure its periodicity. Here, let's show you the package of 2 cups first, and then we get this structure. If he goes to match it with the brigade now, let's take a look at its actual matching rate. This is through this build, and then device to create and connect a device. What we create and connect is a period of a Mountain Meiji structure, and then select this button here, and then select the final structure we just obtained after some operations. We choose the final knot, the structure to be used finally, or build it, and then click on this preview, and it will come up with this adaptation rate.
Then we can see that through this operation, we can get one with a relatively small adaptation rate. If its interface is ready, there will be a small dominance rate, and then click build.
In this, we can, if we need to operate it, we can first convert it into the molecular model, or move its electrode, or copy the left electrode to the right. That is, keep its electrode in a symmetrical structure. These are all operable, and then we won't give that detailed introduction here, eh?
Then we mainly talk about this process after we get this structure now, as I just mentioned. That is, the middle scattered community needs to add some ring filling layers that are the same as the electrodes. And then this ring filling layer is in this simulator. And then click NANODQ add a buffer. This is a case button for adding the ring through layer.
Then this can go through the home. That is, once every point, he will add a layer of this. The rain heel is the same as electronic materials, this and this length. Also through us, we add different lengths first. That is different loop through layers to test, it is to calculate its trial distribution.
Therefore, after performing trial distribution, we can thoroughly assess whether the Holmes length is adequate. Through comprehensive testing, we determine the results.
Even when using our initial approach, incorporating these 6 achievements effectively blocks it entirely.
The influence of both sides, then we will give you a brief try here. That is, you can collect and delete this yourself and then calculate its real distribution to finally determine the length.
Next, press build, which will now create a time-dependent model. The inter-device model captures the previously discussed intermediate interface length. While we didn't explore its exact position, building this model enables customization of distances. As stated before, you can transform it into a molecular model initially, adjust its placement, and modify its perspectives accordingly within this space. Utilize a ruler for measurement and freely select a bird. The fixed distance between 2 atoms is used as a base measure. Once you explore alternate distances, ensure to refer back to this consistent fixed point for accuracy.
That's it. Please shoot the distance. We won't delve deeper into the specifics at the moment. Post obtaining the device model, initiate relevant calculations, and review the associated input file for detailed insights. The Oolong Sutra is this.
What about the inside? The parameter settings will also be introduced in detail in that manual. If you don't understand, you can go to that manual and have a look.
First, deselect GCO, then select the generator after configuring all parameters correctly. This will create the model for the period indicated to the left, comprising the left electrode, right electrode, and other components. What about the intermediate period? The input file is this SCF point input file.
We're going to count that.
That is, before calculating the weapon and sword, you must first put the left and right electrodes. Leave it to his own approach, as evaluating heat dissipation in the central region necessitates employing specific marginal conditions. Subsequently, access and inspect the relevant contents in that section in depth. The parameters not available here are the ones we just selected.
Below is a detailed coordinate file containing XYZ data of its atoms. The file specifies 3 motors and 36 atoms. It is comprehensive and structured for immediate use. If modifications are necessary, you can directly access the file location from this platform with ease.
Right in this place. In this place, for example, if you want to modify its parameters, you can modify it here. After the modification is completed, it can also, let's modify this parameter, for example, then guarantee it.
Yes, and then look at his input file.
It has been changed to more than 10 households 5 times, but it cannot be changed directly in this place. You must go into the folder to modify it. Then after getting this input file, let's demonstrate it here first. For a moment, it is to use a standalone board to perform calculations. He may take a long time to calculate, and then we don't need to wait for his results later, so we will tell you that this process is that if you use the standalone version, you can right-click and then mess up directly. Additionally, when conducting other calculations, utilizing supercomputing provides a noticeable speed advantage over a single computation process. Once submitted here, the calculations initiate promptly. Clicking this function allows you to observe real-time progress, albeit requiring a moment of patience. He is now executing.
Jason,
In fact, this is the process of our approximate calculation. For example, we first perform a calculation on the left and right electrodes, and then after the calculation is finished, we use the same method to calculate the sincerity, that is, the final calculation will get that. Nanot objective. We mainly have all the results, which are also in that file, and then we need to use that later to calculate properties and other things. After attaining self-consistencies, preliminary trial division is calculated to ensure the adequacy of the buffer layer, stabilizing further computation significantly. Yes, and then if it's enough, we can directly use this model to calculate its properties, eh? Yes, this has come out. He is calculating the process. That is, he is already calculating it now. However, he calculates the opportunity a little slower, and then he needs to wait here, so we won't wait, just stop it for him. Then we can also take all the generated files to the computing platform for calculation, which will be faster, probably. Okay, there is another, that is after coming up with this private, don't we have to calculate the computer current and other properties later? We are in this analysis, in this place to elect what we want to count. For example, we want to count its construction now. Yes, the first thing to calculate is its potential, and then the other thing is its density. We just select one. At the same time, let's select this computer first. After you select it, click this right arrow, and then it will come out here. You can set the parameters here at will. If there is something wrong with the settings here, you can change it later. Then we ourselves in 3 steps. After generate, he will come out here. You have to enter the file there and then click the email, run in the same way, and it will start running. Then OpenWays can already view the parameters inside. If you need to modify them, it will also, the same operation as just now, is to open its path and change it in its folder. Then you can change it in this place. Parameters can all be selected accordingly. Then if you save it after losing and changing it, that's not what we changed to. We'll examine from this point. If you are looking at it, he has already changed it. That is, we just changed it, and you can see it here. Well, then probably this process includes its modeling and calculation, and its number files can be implemented in this DS. Then the calculation is about modeling, and it also generates book files. In fact, in DS, it uses this NANODCAL for calculation, and then there is nothing else. Modeling and calculation are probably a process. Then if you have any questions, we can definitely communicate again in more detail, all right?
Okay, let's carefully examine the message box located on the right-hand side.